Hello, good people. Welcome to video number one. And in this set, I'm going to combine 6.10 and 6.12 together. They both take us to some integration techniques. This first part, 6.10, is going to remind us of some skills that we learned in Algebra 2 that could help us now rewrite an integral in order for us to take the antiderivative, if we have to take the antiderivative, right? And with some of the problems, all of the problems that we're going to do, we have to take the antiderivative. And so we talked about use substitution already. But what we're going to see, and one of the reasons why I'm putting 610 and 612 together, is because we're taking the antiderivative of some kind of rational function. So rational function meaning there's a ratio of something on top over something on bottom, right? There's some people call rational functions fractional functions, but the proper name is rational functions. So number one, number two, I have rational functions there. Number three and number four, I have rational functions there. And so the key to anti-differentiating these is to figure out what type of situation am I working with. And so we're going to start by going back in time to Algebra 2 and doing some long division. Because what I notice is when I have a rational function where the numerator is a higher degree, meaning that the biggest exponent on top, that would be this, is bigger than the biggest exponent on the bottom, right? I can divide this out and make my terms a little bit easier to work with. Finding the antiderivative of this, first of all, remember, just like taking the derivative, I cannot take the derivative of the top over the derivative of the bottom. Taking the antiderivative, I cannot take the antiderivative of the top over the antiderivative of the bottom. So I have to change the way it looks. And so we're going to do some long division. And just a reminder of what long division looks like. So when I do division, I'm saying this whole thing is being divided by that. We call this the dividend is being divided by the divisor. And so we're going to take this, and I want to make this little, it's not a square root, but it's like a little square root looking thing without that check mark part. And I'm going to slowly figure out what times x will give me whatever the first term here is. So here's the question. What times x would give me 3x to the third? What would I multiply times x? So whatever's here times this should give me the orange part. And if you said 3x squared, you'd be correct. 3x squared times x does give me 3x to the third. But if I multiply it times that, I have to multiply it times this minus 2. And when I multiply this times this, I'm going to get minus 6x squared. So the first part is I'm always looking to match or to find what times the first term gives me that first term that I'm working with. And then I distribute and multiply that times the second term to give me the second term. Now here's the part that sometimes trips people up. We have to subtract this whole thing. Well, if I'm subtracting the whole thing, that means I'm subtracting the 3x cubed and I'm subtracting the minus 6x squared. And so what some people do, I lost some things there. What some people do is they just change the sign and they say, well, I'm subtracting this and I'm subtracting this. So now it becomes a plus 6. Why do we do that? Because this will reduce. But here I'm left with 5x squared and then the remaining pieces over here. And now we start the process again, except instead of asking what times x gives me 3x cubed, I'm asking what times x gives me 5x squared. Well, that would be positive 5 or plus 5x, right? Plus 5x times x would give me 5x squared. And so I write that here. But then I also have to distribute this times the minus 2, and that's going to give me minus 10. I do the subtraction, so minus 5x squared minus a minus 10x, that's going to change it to a plus. And then I get the leftovers here. So this is going to be 5x plus 1. And then I ask myself, is it possible for me to do something times x that would give me 5x? Sure. I could multiply it by 5. 5 times x would give me 5x. 5 times minus 2 would give me minus 10. And I subtract. minus, minus, but it's already minus, so it becomes a plus. And here I have 11. And at this point, I realize there is nothing that I can multiply by x to give me 11. Or rather, there is no positive powered term that could give me that, right? I guess I could use some kind of negative exponent that would give me that, but we're not talking about that. The other part is I notice that once I get to a constant up here in my quotient, in my answer, then I can stop. This is what we call the remainder. And the remainder is a fraction of what I was dividing by. And so then I add on this fraction, 11 out of x minus 2. Okay. All of this work was just to rewrite this fraction or this rational function as 3x squared plus 5x plus 5 plus 11 over x minus 2. This is the key to using log division, is that when we divide things out, we're going to get some nice terms, and we're going to get a little rational function here. But this rational function is a lot easier to work with than this one. Okay, now I'm ready to take the antiderivative. And if you want, you can do individual antiderivatives. I'm just going to start taking the antiderivative here. So I'm going to add 1 to the exponent and divide. You know what? Let me change the color so that we can see that now I'm working with the antiderivative. Add 1 to the exponent, divide by the new exponent, plus 5x, add 1 to the exponent, divide by the new exponent, plus 5x plus, now here, let's think about what we're looking at. We're taking the antiderivative of 11 over x minus 2 dx, right? That's the last part right here. If I factor out the 11, then I'm left with 1 over x minus 2 dx. And if I use u substitution, where u is this part, and du is going to be dx, then this becomes 11 times the antiderivative of 1 over u, and that's just going to be the antiderivative of 1 over u is the natural log of the absolute value of u. There's an 11 there. And then I know that u is x minus 2. So my final antiderivative here would be 11 times the natural log of x minus 2 plus c. I'm able to take the antiderivative by doing long division in order to simplify my integrand. Integrand is what I'm taking the integral of, this thing. And then I can take antiderivatives a little bit quicker. So I do some work at the beginning to make it look a little bit simpler so that I can take the antiderivative. When do I do that? Usually whenever the numerator power degree is bigger than the denominator degree, right? If the top numerator has a bigger power than the bottom, then we might need to divide it out. We could also try to factor, but I wasn't sure if we were going to be able to factor, so I just used long division to get the answer. This is the antiderivative. We'll come back in the next video, and we'll do number 2, kind of the same idea, but now we know what the process is going to be.